All right. This video is to help you understand the nature of chemical equilibrium. So till now, the kind of reactions that you have been looking at were completion reactions, right? You learned about that in the previous lesson. So completion reactions till now, all the reactions that we have dealt with generally were completion reactions. Basically, you start with the reactants, say A plus B. They go in only one direction and they give you the products C and D. This is how a completion reaction, we have been representing all reactions. The reaction, the change occurs in only one direction. So by the time the reaction is all done, generally, most of the time, the reactants are all used up and the products are formed. Okay. In this now in this unit, we are trying to look at a different type of reactions. These are called reversible reactions, and reversible reactions, they are different than completion reactions in that if you start with the reactants A plus B, initially the reaction goes in the forward direction and you form C plus D. But after some point, when a certain concentration of products has formed, the reverse reaction starts. So a reversible reaction is represented in by a double-headed arrows, meaning the change is happening in both the forward, where A plus B combine to form C plus D, and then at some point C plus D break down, combine, whatever, to give you back the reverse reaction to give you A and B. So reversible reactions happen in both directions. So reactants combine to give you products, products break down to give you back reactants, and the reaction continues. So these reactions never come to an end, they never stop, and these kind of reactions are called reversible reactions, right? The only thing that happens with reversible reactions is they attain equilibrium, and this is a kind of equilibrium that we say they achieve dynamic equilibrium. That's what you have learned till now about these types of reactions. Completion reactions go to completion, they achieve static equilibrium. So that's it. Reactants give you products, nothing else happens after that. Once all the reactants combine and they form products, the reaction is done. That is it, it's all over. But for reversible reactions, reactants combine to give you products, and then the products break down to give you reactants, and this goes on for a time till dynamic equilibrium is achieved. Okay, so let's look at this in a little bit of a detail. All right, so for completion reactions, right? So if I try to plot the concentration of reactants or products, doesn't matter what it is. So concentration in, say, moles per liter, right? And time, concentration versus time, say time in seconds, minutes, hours, whatever, it doesn't matter, some time unit. So for a completion reaction, initially you start out with the reactants, right, at a certain concentration, whatever they are. So with time, the concentration of the reactants falls, it falls till the reaction comes to completion. Most likely the reactant concentration goes to zero if you have really done your stoichiometry well. Otherwise, you will have one reactant that has been completely used up and something is left over, maybe. But some reactants, at least some reactants concentration goes down to zero. On the other hand, your products start out at zero, the concentration, and they plateau out. So at time t, when your reactant goes to zero, your products are max. So this is what the concentration versus time looks for a completion reaction. If I did drew a graph for the exact same one for a reversible reaction, say, and I'm plotting again, same thing, concentration, moles per liter versus time in seconds, hours, minutes, whatever. I'm choosing seconds. So what happens for reversible reactions is initially the concentration of the reactants is whatever it is, right? So say max. As time goes on, the concentration of the reactants falls and it plateaus out. It doesn't reach zero, as you see that. For products, they start out at zero initially, right? And then their concentration with time goes up, and there it is. So this is a big difference between a completion and a reversible reaction. The reactant concentration never gets to zero for a reversible reaction. On the other hand, for a completion reaction, it goes to zero, and we say it achieves a static equilibrium. On the other hand, reversible reactions, we say that they achieve a dynamic equilibrium. I'll explain in a second what we mean exactly by that. So there. So this is it. So this is, if I plotted concentration versus time for completion and reversible reactions, this is how the graph would look. Let me do something else. For this, on the other hand, if I wanted to plot the rate of the reaction versus time, whatever the unit of time may be, for a completion reaction, what happens for completion reactions? We start out with a certain reactant. Remember when we did that sodium bicarbonate and vinegar, so acetic acid, the reaction rate initially was very high, right? And then as time went on, it slowed down, slowed down, slowed down. For a completion reaction, the rate goes to zero. At some point, whenever the reactants get used up, the rate goes to zero, right? Rate equals zero. On the other hand, if I plotted this for a reversible reaction, I start out initially, suppose I'm following the rate with respect to the change in concentration of the reactants. Say, initially the rate is very high, right? And then it plateaus out. Initially, the rate with the products is zero because initially you're waiting, the reactants have to combine to form the products. So initially, since you have no products, the rate is zero with respect to the products. But as the concentration of the product accumulates and the reversible reaction starts kicking in, the rate slowly picks up and the rate increases till it plateaus out. Okay, so this is how if I plotted the rate versus time for a reversible reaction. So initially, with respect to the reactants, I should have used a different color, right? So let me say this is reactants, rate with respect to the reactants. Initially very high, comes down to a plateau. Rate with respect to the products, initially zero, but then picks up and then plateaus out. So this point where the rate of the forward reaction, rate with respect to the forward reaction equals the rate with respect to the reverse reaction. Do you notice that the rates are equal? So this point where, so basically at the time where the concentration, the rate of the forward reaction equals the rate of the reverse reaction, we say that equilibrium has been achieved. At this point where the rates of so when equilibrium has been achieved, this is dynamic equilibrium. Chemical equilibrium is always dynamic. So chemical equilibrium, when equilibrium is achieved, rate of the forward reaction equals rate of the reverse reaction. So what do we mean? So basically, both reactions, as you see, the rate has never become zero. For the completion reactions, rate hits zero. But for the reversible reactions, rate never hits zero. So when equilibrium sets in, rate of the forward reaction equals the rate of the reverse reaction. So basically, the change in concentration there is no change in concentration when equilibrium hits for products or for reactants. So concentration of the reactants remains static. Concentration of products remains static, meaning it doesn't change. But the rate is not zero. It is not zero because this rate of the forward reaction equals the rate of the reverse reactions. The number of molecules of reactants that are combining to form products is pretty much the same as the number of molecules of the products that are breaking down to form the reactants, meaning the reactions haven't stopped. They're going, but they're going at the exact same rate, forward and reverse. And that's why there is no change in concentration of either the reactants or the products. So let me state that clearly. Okay. Actually, you know what? I like this rainbow pen. All right. So when chemical equilibrium hits, chemical equilibrium is a dynamic equilibrium. So when equilibrium hits, so rate of the forward reaction equals rate of the reverse reaction. Concentration of products does not change once equilibrium hits. Does not change. When equilibrium hits, concentration of the products does not change. Concentration of the reactants does not change. So some product molecules tend to form reactants, break down to form reactants. Same number of reactant molecules turn into products, and therefore there is no net change in the concentration of the products or the reactants. The rate is not zero. The processes are still happening. They just happen to happen at the exact same rate. That is dynamic equilibrium. Okay, all chemical equilibria are dynamic equilibria for reversible reactions. For completion reactions, it's static. But this unit is all about reversible reactions. Reversible reactions achieve a dynamic equilibrium. Okay, so now mathematically, if I wanted to represent, we need to know, chemists need to know something a little more quantitative ideas about dynamic equilibrium. So when dynamic equilibrium hits, when chemical equilibrium hits, we can represent mathematically the chemical equilibrium with this. So for a reaction that is of type, say, A plus B gives you C plus D, and I have the balanced equation, say MnOP, say, right? These are my coefficients in my balanced equation. So chemical equilibrium can be represented mathematically. Quantitatively, we can come up with a constant. This is called the equilibrium constant. You know, K is a constant, right? Because we're talking about equilibria and chemical equilibria, this is the equilibrium constant. The equilibrium constant is measured as concentration of products, so B, raised to their coefficients from the balanced equation. So, oh my, sorry, this needs to be concentration of my products, which is C raised to O times D raised to P. That's my concentration of my products raised to their coefficients from the balanced equation over concentration of my reactants raised to their coefficients from the balanced equation. Okay, so this is how we represent mathematically the equilibrium constant, which gives us an idea of concentration of products versus the concentration of the reactants. So this is products versus reactants. Mn, O, and P are the coefficients from the balanced equation. Okay, you do remember square brackets means concentration. Now, if we're talking about concentration, guess what? KEQ has to be determined experimentally. That is why, because concentration of products, you need to measure it. So determined experimentally. All right, so the equilibrium can be, we have a measure, quantitative measure of equilibrium by talking about something called an equilibrium constant, KEQ, which is a ratio of concentration of products to reactants raised to their coefficients from the balanced equation. KEQ has to be determined experimentally. Now, there are a few things about KEQ. The value of KEQ gives us a good idea about the concentration of the products and reactants. Now let me switch my screen. The value KEQ, here I go. KEQ is the symbol for the equilibrium constant. It's a ratio comparing the concentration of the products to the reactants in a reversible reaction. It is temperature dependent. because as you know, rate is temperature dependent. So KEQ is also temperature dependent, the different value of KEQ for different temperatures. It must be determined experimentally. Now, the general equation, suppose I have something like this. The equilibrium expression becomes KEQ is product concentrations over reactant concentrations raised to their coefficients from the balanced equation. Of course, you know that. Now, KEQ, to determine the value of KEQ, we have to write a balanced equation. You have to write an equilibrium expression. In this, when we write the equilibrium expression, you have to be really careful. We do not include the concentration of the solids or the liquids, because technically the concentration of pure liquids and pure solids does not change. So the only substances whose concentrations you are going to include in your equilibrium expression are aqueous substances or gases. Those are the only two things whose concentration changes. So be so just be careful. Do not ever include the concentration of the products or the reactants. Sorry, a concentration of pure solids or liquids. I'm sorry. Concentration of pure solids or liquids do not feature in the equilibrium expression. We plug in the concentrations and we solve. KEQ does not have any units. You need to remember that. Okay? So KEQ does not have any units. In our equilibrium expression for KEQ, we do not include concentrations of pure liquids and solids. We only include the value of aqueous substances, concentration of aqueous substances or gases, because these are the only two things whose concentrations change. Okay, the value of the equilibrium constant the value of KEQ is really helpful in figuring out. I'm playing around with my pen. I'm trying to figure this out. Give me a second. The value of KEQ tells us something about the reaction. If the value of KEQ equals 1, that means when equilibrium is achieved, the concentration of the products equals the concentration of the reactants. That means in your reaction mixture, you have a 50-50 amount of products and reactants. Okay? Because you remember, KEQ equals concentration of products raised to their coefficients over concentration of reactants raised to their coefficients. Therefore, if KEQ equals 1, that means products concentration equals reactant concentration. In the reaction mixture, you have a 50-50 ratio of products and reactants. If KEQ is more than 1, that means your concentration of products at equilibrium is more than the concentration of the reactants. These are the kind of reactions that we are really interested in. If the value of KEQ is way more than 1, that means when equilibrium is established, for all reversible reactions, equilibrium is established at some point or other. When equilibrium is established, concentration of the products is way more than the concentration of the reactants, and these types of reactions are said to be product favored. Okay, these are the kind of reactions that chemists are generally interested in, because you had at equilibrium the product concentration is quite large. Now, for those reactions where KEQ's value is less than 1, that means at equilibrium, concentration of the reactants is more than the concentration of the products. Such reactions are said to be reactant favored. All right. Again, KEQ is temperature dependent. So is KEQ is temperature dependent when I set up my equilibrium constant expressions, which is KEQ equals concentration of products raised to their coefficients over concentration of reactants to their coefficients. I will not include in this expression, we will never include pure solids or liquids. Okay, they do not feature. The only things that feature in my meaning, I will never put, if I said, if a reactant or a product was a solid or a liquid, I would not feature them in my equilibrium expression. The only thing that would be featured would be aqueous substances and gases. These are the only ones that find a place in my equilibrium expression. All right. So, for example, if I have a reaction, a hypothetical reaction, say A, and say it's aqueous substance, plus B, say it's also an aqueous substance, and I have a reversible reaction set up for products M, say X, and say this is an aqueous substance, plus N, and this one is, say, a solid. When I set up KEQ, and I have to determine this experimentally, right? Because I have to measure the concentrations, my expression would look like M raised to the power of X. At this point, I will not include N because N is a solid, so nothing, that's it. However, my reactant concentrations, A, because it's aqueous, it can feature, and B, this is what my expression for KEQ will be. I will not include N because N is a solid. That's what we mean, that when we say solids, pure solids and liquids do not feature in the equilibrium expression. This is what it means. It means I will not put it in my equilibrium. So if I gave you values, like, hey, this is the concentration, A equals, say, whatever, 2.1 molars, and B equals, I'm making numbers up, B equals 0.5 molars, and M equals 1.2 molars, and N equals 3.5 molars. I will not use 3.5 at all in this expression. It will only be, I'll plug in the value for A, plug in the value for B, and plug in the value for N. Since M for M. And since there is no place for N in my equilibrium expression, I do not ever use N because N is a solid. Same story goes for a liquid. All right.